be riding it?
Well, anytime that you ride a bike, you gotta wear a helmet.
Yeah, but it's not
You
riding.
only get one noodle.
Don't even. Are you gonna ride it? The bike? From there to there? And your helmet on?
Alright, so today we've got a warm-up, and then I think it's 3 examples-ish, something like that. And then it might be 4. Not good with numbers. But a couple of things. First off, tomorrow you have a formative. Okay? And then your test is next week, Tuesday. Okay? So just know both of those. With that being said, through how many radians will the hour hand of an analog clock rotate in 48 hours? Go. Radians. Analog clock, how many times does the hour hand go around in a day? Emma? 2, right? Because it goes around every 12 hours? 24 hours in a day? So in 48 hours, how many times does it go around? 4 times, right? Each time it goes around, how many radians does it go through? 2 pi? Okay? So it goes around, it makes 4 revolutions. Each revolution is 2 pi radians. Means that this hour hand went around 8 pi radians.
Yeah, me too. I thought I started thinking that it went around 48 times.
That would be the minute hand would have gone around 48 times. Yep. Okay. Convert those two to their respective things. We're starting to review for the test, just so you know. So converting to decimal degrees, you're going to have 135 plus 47 divided by 60, because there's 60 minutes in a degree, plus 23 divided by 3,600, because there's 3,600 seconds in a degree. That gets you and so we've been rounding to 3 decimal places. Questions, comments, concerns, clarifications? Okay. I get 78 degrees, 26 minutes, and 6 seconds. Questions, comments, concerns, clarifications? Good? Love it. All right. So, I'll move this one up so that we can see it. Figure showing a chain drive. So this is on a bike here. This is a great representation of a chain drive. Okay? So the the pedal sprocket is at 4.85 inches. The drive sprocket is at 1.54 inches. They're connected by a chain. Okay? So my question is, what is the linear speed of that chain if the larger sprocket, so that we're on this sprocket, is rotated 4 times in 10 seconds? Then I also want you to find the linear speed of the chain if the smaller sprocket is rotated 4 times in 10 seconds. Okay? Everybody understand the problem? Questions on said problem? All right, figure it out. Coming up with 2 speeds there. So we for sure start with 4 revolutions per 10 seconds. One revolution is 2 pi radians. And 1 radian on the big sprocket is 4.85 inches. So that gives me my speed in inches per second. 12.189 inches per second. Smaller one now, still traveling at 4 revolutions per 10 seconds. Still knowing the fact that there's 2 pi radians in 1 revolution. But now 1 radian is 1.54 inches. So that gives me a linear speed of 3.870 inches per second. Agree? Questions, comments, concerns, clarification? A 24-inch diameter car is making, or the tire is making 9.3 revolutions per second. Find the speed of the car in miles per hour. Pre-questions. Before you get started, questions. None? Find me miles per hour. So we're making 9.3 revolutions per second. Each revolution is 2 pi radians. 1 radian is 12 inches. So now I'm in inches per second. So now I got to transport that or change that into miles per hour. So 12 inches is 1 foot. There are 5,280 feet in 1 mile. And there are 60 seconds in 1 minute. And there are 60 minutes in 1 hour. All told, on top, you've got, oops, that's bad, 9.3 times 2 pi times 12 times 60 times 60. On the bottom, that, I get 39.841 miles per hour. Nailed it? Nailed it. Okay. Yesterday, after some extensive research, I found out all of these things about Lance Armstrong and the Tour de France. Okay. So, under this setup, how fast is Lance Armstrong going in miles per hour if he is pedaling at a rate of 7 rotations every 5 seconds? Okay. So let's talk about bikes, since we struggled with this a little bit yesterday. Schmeling brought in his bigger bike today, so that you can see it a little bit better. As always, Jackie, safety first. Okay? So the pedals are going around at 7 rotations, right? Is that what I said? 7 rotations every 5 seconds. Okay? So the pedals are going around. What's actually touching the road? You got the brake. Right here is touching the road, right? Okay? So we have to get from here to here. Okay? We can't jump. We can only travel if we're connected. Right? Okay? So right now, we know that the pedal is rotating at 7 revolutions every 5 seconds. Correct? Okay? So I'm on the pedal. Where do I need to get to? I need to get to the back tire, right? Okay. What's connecting the pedal to the tire? The chain, right? Okay. So we need to find the speed of that chain in, let me rephrase that. Which speed of the chain do we need to find? Linear speed, right? Because the linear speed is the only thing that's going the same distance. AK? Very disrespectful. You're in a better homeroom than that. Okay? So the linear speed of the chain is the only thing is the same all the way through. Angularly, rotationally, they are different. That's why we did that other one when they were spinning at different speeds. Okay? Doing the same if we're same rotations in the same time frame, because they're different sizes, they're spinning at different speeds. Only thing that's constant is the linearness of the chain. So we need to find the linear speed of that chain. So first thing we're going to need to go to is 1 revolution is 2 pi radians. What did we say the radius of the sprocket was? 4.14 inches. Now I'm in inches. Here, let me just cancel these out. Now I'm in inches per second, correct? Is that a linear speed? Yes, that's a linear speed. So now I can go from the pedal to the little sprocket, correct? Yes? Okay, because I'm now connected to it, I can go to that one. All right, so now I'm on, with this setup right here, now I am right here on this sprocket. Okay? I need to get out to here. What is the same on this sprocket as this outer edge of the tire? Angular speed is the same. Diameter of this sprocket is this much. Diameter of the wheel is this much. Okay? So the angular speed, because they're both, sorry, I'm trying to keep the bike without falling down. The tire here and that sprocket are spinning at the same speed, angularly, because they're on the same axle. Okay? So now I need to go from this linear speed of the chain to the angular speed of the small sprocket. Radius of the small sprocket was 0.81. Now I'm in angular speed of the small sprocket, which is also the angular speed of the outside of the bike tire. Okay? So now I'm in the angular speed of the bike tire. Okay? So that now needs to be converted into miles per hour. The radius of the bike tire was 12.8 inches. inches per second now needs to be converted into miles per second. Now I'm in miles per hour. Should get 32.698 miles per hour. Two things for the remaining time. First thing is, up here, we have an extra credit opportunity for you if you so choose. Okay? We call it the Huff and Gasper problem. You'll see what it is all about. It's all about speeds and rotational speeds and angular speeds and miles per hour and all that fun stuff. This is due on Tuesday if you choose. If you want to, come on up and grab one. You have the remaining time to also work on your homework packet, which is also due on Tuesday.